So you might ask why somebody from Fresnel Technologies is talking about freeforms. Well, of course, we make Fresnel optics, but we also make non-Fresnel optics. So I wanted to talk to you a little bit about a project that we did a few years ago on a freeform laser scanning optic. It really kind of illustrates a lot of the things that people have been talking about through this time with being able to reduce weight and volume, difficulties with metrology, etc. So the problem we needed to help our customers solve is making a compact laser scanner with the laser power. So the fast axis of the laser diode is first collimated by a glass cylindrical lens that's separate from this. And then that partially collimated light passes through each of these lenses in turn as the optic spins. The laser gets gated on and off just before and after the transition between each lens. And each of these lenses is a cylinder, a toroid, translated in this way along this 43-degree angle. And so this one makes a spot over there, and this one makes a spot over there, and this one makes a spot in the middle. They're not in order. It jumps around in the 12 spots, but it makes 12 spots in a line about 2 centimeters long. Each surface of each lens has a different prescription, so there are 24 of them in total. That means that for each cavity of the injection mold, we need to make 24 separately diamond-turned inserts, each of which has a different freeform prescription on it. And then we come to the problem that everybody has, which is how do you measure this thing? And it has even worse problems than usual because you need to make a lot of them. So you can't take 6 months to figure out how to measure it and then 3 months to measure it. It's very constrained. It has steps in it. So the first thing we tried was looking at it with our SmartScope video microscope, dust some aluminum powder on it to give the surface some contrast and let you pick it up with the focus. This is one of the lenslets that was demonstrated through other methods to actually be working pretty well. We made the measurement on the SmartScope, got this point cloud you can see on the left, compared it to what we thought the shape should be on the right, and you can see that there are places where the comparison is missing. There are some deviations that are claimed to be 25 microns or so apparently large differences, but the lenslet was working well. So what's the problem? Alignment problems. This method just doesn't work very well. We decided to stop messing with this and move on. So then we tried our TallySurf, as most people probably would have, using TallySurf software and also some custom code to analyze this. The TallySurf has a lot of challenges with the probe colliding at the steps, so you can't get all the way to the edge of the lenslet. The probe also tends to fall off the edge. And a number of these lenslets don't have the peak of the A cylinder on the lenslet. It's off the edge in space. And so to the extent you can do analysis in the TallySurf software, it's not really available when the peak of the curve is off the physical surface, or at least it wasn't when we were doing this. So you can see an example of this on the right. We had have a y-axis on the TallySurf, so we were able to move across, gather some data, and the top is the fit, which didn't really work terribly well. It has a big hole in it where it couldn't figure out what the surface ought to be. The comparison on the bottom looks pretty good, but there's some holes in the data, and it can't measure anywhere near the whole surface. We also tried our new view. Has a bit of the same problem, especially on the inside of the flower. You can't measure the whole surface without collisions. So where did we wind up going? We wound up with a functional test, essentially. It's a little bit difficult, obviously, to decide exactly what you should do with your process, but you at least can find out whether you have a good process. So we found that the bad lenslets, and explain the functional test a little bit, this is actually the laser scanner. These pictures are of thermal paper, so there are little burned spots on the thermal paper that where we got the laser to fire 12 times as it went around. And you can see on the upper right that some of the spots in each row, this is 3 different samples, one of which has been done twice. Some of the spots in the row are small and round like they should be. Some of them are very elongated, which is not good because we need the laser light in a small spot so that it will make the appropriate little burns and make the wrinkles tighten up on your skin. So we can tell that it's bad. We're able to adjust the process and get to, on the bottom, good, nice, small, slightly oval spots, evenly spaced. The numbers on the bottom are every 500 pieces. We provided a sample and took the data. So we were able to use this method to tune the process and to monitor production. So, and I'll conclude, freeforms can definitely significantly improve the system size and weight. Don't know how you would do this otherwise. A big galvo or something, I don't know. Mold making and the molding for this are very complex, but the metrology is even more complex. Functional test worked well for us here, and we've made about 200,000 of these so far, 24 freeform surfaces each. I think Meta and so on may have made more freeform surfaces than we have, but I'm not sure, 4.8 million. And I want to give a lot of credit to my team at Fresnel, especially Oscar Lechuga and Dr. Margaret Freilich, who did a lot of the mold making and molding and analysis.